Hi everyone. Well, I guess we're starting triple integrals or volume integrals, right? So on the left here we have just a quick review of what we did with double integrals. First, well, I don't know if it was the first thing, but one of the first things we did is think about integrating the number 1 over some region R, right? And when we do that, the double integral of 1 is just the area of that region. So if you want to calculate the area of this region R, this little green region here, this thing here, yeah, just integrate the number 1, right? Or, think of 1 as the height above the xy plane, right? So technically it's a volume if you look at this down here, right? If you're integrating a function that's not just 1, then you're getting the volume underneath the surface, right, where z equals f of xy is the surface. And you're getting the volume of this little purple region down here underneath the surface, but above the region R, right? So it's some sort of a column. It looks like a, looks like a cylindrical type column here. Kind of hard to draw, but that's the idea. Maybe use a lighter color here. So yeah, this will be some region, solid region, and we're getting the volume of that, right? Okay, so we did that in the last couple of videos. So now that we're going to transition to triple integrals, and we can sort of do the same thing here. We can think about this solid region now, right? So we're using Q instead of R, Q for a solid region in space, right? So again, I'm trying to make this, three-dimensional here. Imagine that this is some blob, three-dimensional blob in space, right? And you want to know the volume of that. Well, then just integrate the number 1, right, as the triple integral, right? So we use dv for volume, right? Right. We'll talk about this in a little bit, but dv could very well be, dx, dy, dz, right? Or it could be dz, dy, dx, or any permutation of these. There's 6 of them. So we'll probably use this one the most often, but the idea is you can switch them. Right, so that's just the idea of getting the volume of a region in space, right? So don't get confused between getting the region this way. Right, after all, this region Q up here does not have to be, underneath any surface, right? It's very difficult to see what the surface here is, right? So, of course, this, right, getting the volume of this, we can think of this as a triple integral now. How? Well, we're thinking about this the following way, right? We have the region R, and then the third integral here will be from z equals 0 to z equals the surface, f of xy, right? And then you're just integrating 1, let's say dz, dy, dx, right? And then the dy, dx, those integrals here will be over the region R, which you have to, parameterize some way, right? So yeah, you can think of what we did before, the double integral, by just adding that 1 extra integral here, we can make it into a triple integral. But it's the same thing, because when you do that first integral, right, in other words, when you evaluate this, the dz integral here, all you get is the double integral over R of f of xy, right, minus 0, dy dx, which is dA for us, right? So you just recover the original double integral to get the volume. Just keep in mind that that only works for the region that's underneath the surface. this region Q up here, this region here, does not look like it follows that pattern here, right? It's not a cylindrical column, right? Okay, right. So now comes the tricky part. Now we want to talk about doing a triple integral over some solid region Q of some function. Say f of x, y, and z over, dv. So dv is again dz, dy, dx or something like that, right? But again, this is just the idea of a triple integral of some function. Well, the problem with that is this interpretation here as volume doesn't make sense. If a double integral of some function gives you the volume, the triple integral of this new function, f of x, y, z, gives you what? Well, it gives you the four-dimensional volume, right? Of the region between Q and well, it's the right. So yeah, above the region Q, but below the surface. So of the region, again in quotes, above Q and below the surface. Well, it's not a surface anymore, right? It's now the volume. W equals f of x, y, and z. Got that? So yeah, we need the w axis. Where's the w axis? We have the x-axis coming out of the screen at you. We have the y-axis going right and left, the z-axis going up and down. Yep, there's no w-axis. I can't draw it, right? We already have the three perpendicular directions. So, right, so this is something that I can't visualize. I don't know how to interpret a four-dimensional volume. But that's what it is. That's just the interpretation of it, right? So yeah, there's got to be a better way to sort of visualize what's going on with these triple integrals here. Right. So before we get into any computation, right, let's just see what this triple integral here, what does this even represent? If we can't think of it in terms, of a four-dimensional volume, right? So it won't be, square meters or cubic meters. It'll be in quartic meters, right? So meters to the fourth power. Again, I can't visualize that at all. All right. So yeah, let's go back to the double integral for a second. Right, because there is another interpretation of this which doesn't require three dimensions, right? You just have some region, R, in the xy plane, right? And let's suppose it's just a flat piece of material, right? Different densities here, right? So if we're thinking of f as the density function over the region R, remember I use sigma for density. The book uses rho for density. So maybe I'll go back to rho for density, right? So rho here is the density at the point xy. Okay, so different points give you different densities, right? Okay, so what is this, right? This is m, right? This is the mass, the total mass of the object over this region R, right? But it's a flat object, right? Like a pancake or a coin or a piece of paper, right? Something flat. Right. So now we can easily make the transition here to the triple integral, the volume integral here. So now we have, instead of some flat region, we have some solid region in space, right? You know, the best example, if you want a nice symmetric one, is just a sphere, right? Well, the sphere is the surface. What I mean by that is the ball, the solid region inside the sphere, right? So yeah, these are now solid regions. So we're going to use, we're going to use Q for the solid region now, right? And you can imagine, right, a uniformly dense sphere, right, where the density is the same everywhere. Or you can imagine, just like in the two-dimensional case, where different regions have different densities. Some parts are more dense than others, right? Maybe to be a little more exact here, let's say the solid is very dense at the center and then less dense as you go out radially. So at the surface, it's not very dense at all. But inside, and when you get to the center, it's more dense. You know, like the Earth itself, right? The greatest density is at the center of the Earth, and it's less dense the further out you go. All right, so we have some density function, I'll call it rho, as a function of x, y, and z. Right? And if we do a triple integral of that density over the volume, again, we get the mass of the solid Q. Right here, we just get the mass of the region R, the flat region R, the planar lamina, as the book calls it, the planar lamina. Yeah. Right, which is just a flat surface, right? Okay. So, yeah, so when we do a triple integral of some function, think of that function as just some weight that varies over the region, and you're integrating over that region, Q, and you're just adding up all these little weights at each point. Right? Density is, I think, the clearest example of what kind of a weight could be. The different regions have different densities. Right? So I think with that, we can dispense with this four-dimensional volume, which I have a hard time figuring out. But if we think of this f now as like a density function, then it sort of makes sense, right? It certainly makes sense in 2 dimensions, and you can easily extend this notion to 3-dimensional objects as well. Okay. And then later on, of course, we'll talk about center of mass as well as moment of inertia, as we did a couple videos ago for flat regions. They extend in much the same way to solid regions as well. Okay, so before we do all that, let's just do some examples of triple integrals, or maybe better yet, let me give you the definition and then how to actually evaluate these triple integrals. So here's the definition from the book, and the basic idea is you have your solid region, and you just divide this up into little, not squares, but little cubes, I guess, or little rectangular pieces here. Right. So that is your delta VI. And over that small cube, you have some function that has some value there, right? And at each cube might have a different value. That's why it's a function of position. And you're just adding all these up, right? You're just adding them all up and making them smaller and smaller so that delta V goes to 0, or effectively it becomes dV, and then that's where you get the triple integral, right? Right. And again, if you're just integrating 1, you're just getting the volume. Okay, so let's not worry too much about the definition here in terms of this limit of the Riemann sums. We've talked about that, in Calc 1, and there's no reason to get too deep into this unless you want to go into analysis. Right. So for our purpose, these interpretations of getting the mass, integrating the density to get the mass, or integrating 1 to get the volume. But if you integrate the function, right, some volume f region over some region q, you get 4-dimensional volume. Right? So we're not going to worry about that, though. But density and mass is a good analogy here. Okay, so now we can talk about how do we actually evaluate the triple integral. And so this is effectively Fubini's theorem, right? What this is going to do is allow us to calculate the triple integral over some region Q of some function, let's say f of x, y, and z, times dv, right? So again, it depends on how your region Q is defined. So we're going to define it this way, and this is the usual way. Hopefully, most regions will be defined this way, right? And the idea is, so x varies between a and b. That's the x-axis here, right? And then y varies between some curve, say y equals h1 of x and y equals h2 of x. So I drew these little purple curves in the xy plane. And then z varies between two surfaces, right? So this is the bottom surface, g1, and this is the top surface, g2. So we're assuming g2 is greater than g1. And z is just everywhere in between, right? So in other words, the region Q is really this region here between the two surfaces, but above this blue region down here, right? So only above that region. In other words, we're not counting between the surfaces over here because that's not above our region. I hesitate to call this R here because that's from double integrals. But right, this region here then would be your Q. Okay, and if f is just 1, then you're just getting the volume of that region Q, right? But if f is not 1, if f is, say, the density function, then you're getting effectively the total mass of this solid region over here, right? Okay, so we can evaluate this by doing the iterated integral. The outer one is just x goes from a to b. The middle one goes from h1 of x to h2 of x. So these are y's, right? And then the first integral, the most inside integral, goes between the surfaces, g1 of xy to g2 of xy. Right? And then you integrate your function with respect to z first, right? Then y, then x. Okay, so this is the standard order for regions that are defined in this way here. Right? Of course, you can define your region in other ways, but this is the most common, and this is the one you want to see. Because if it's defined some other way, it might not be quite as simple to evaluate, depending on if your surfaces are, say, y as a function of x and z, right? Then you're just reorienting this thing around. So yeah, we'll see how to do that later. How to change the order of these dz, dy, dx. Not easy in general. Okay, so before we get to calculating triple integrals, I just want to go back to what we did a couple sections ago, right, where we talked about the mass of a planar lamina. So now Q, of course, is a solid region. So now we're getting the mass of a solid region, which is, a little more practical since most objects are three-dimensional, right? So calculating the mass, we already did that interpretation, right? If you just integrate the density over the volume, you get the mass, right? The total mass of that object. And then we can calculate the center of mass, right? The center of mass is now going to have three coordinates, x bar, y bar, and z bar, right? For a planar lamina, there was only the x bar, y bar because it was an object in the plane. It was a two-dimensional object, right? So now we have a three-dimensional object. We have three coordinates for the center of mass. And the x-coordinate is, well, here. It's just 1 over the mass times the triple integral of x times rho, rho being the density. I know on my formula sheet, of course, I used sigma. So let me just make that clear that rho is the density function, right? Not the distance from the origin. So yeah, don't get those two mixed up. This is not spherical coordinates yet. So rho is the density. On my formula sheet, though, I use sigma, if that's okay, just because I don't want to get it confused with distance. So either way, sigma or rho is density. Okay, so yeah, x bar is just 1 over m times the triple integral of x times the density. Y bar is 1 over m times the triple integral of y times the density, and same thing for z, right? Right. So again, this is how I remember it. The book uses the first moments of mass. I'm not going to even bother here. But if you want to do it that way, or if that's how you remember it, then that's fine. Right. So these are the formulas for the center of mass. Right. And of course, you can also calculate the moment of inertia. When you're rotating about the x-axis, y-axis, or z-axis, you get three different formulas. For the y-axis, for the x-axis, the moment of inertia is just the triple integral, right? There's no 1 over m here. Triple integral of y squared plus z squared, which is just the square of the distance from the x-axis. It's the square of the distance from the axis of rotation, right? So for the y-axis, you get x squared plus z squared, which is the distance, the square of the distance, rather, from the y-axis. And I think the one we're going to use most often is rotating around the z-axis. So if this is the z-axis, that's the axis of rotation in most cases. And the distance from the z-axis is x squared plus y squared, right? So you multiply that times the density and then integrate that over the region Q, right? So we'll try to do one of these examples a little bit later, but before we do, let's just evaluate triple integrals. Right, so here's our first example, and we're just going to evaluate the iterated integral. And I just got this out of the book. It's one of the homework problems. And I'm hoping a fairly routine one, right? So the way you evaluate iterated integrals is much the same way that you evaluated double iterated integrals. You start with the inside integral, right? You always start on the inside. Maybe I'll do that in orange here, right? And then we'll take care of the other two integrals later. So we'll leave the 0 to 9 for x, and then 0 to y over 3 for y. Oh, I'm sorry. I mixed up the order here. It's dx and then dy. Yeah, if you're integrating with respect to y, you can't have y as one of your limits, the upper limit of integration. So yeah, the order is dz, dx, dy, not dz, dy, dx. So make sure you realize that. I made that change there. Oops. Yeah, put the y back. All right. So now we just do the inside integral here. So you integrate z with respect to z, and no surprise, you get 1/2 z squared. And now we just evaluate that between 0 and the square root of y squared minus 9x squared. So when you plug in 0, you just get 0. When you plug in the square root and you square it, that cancels the square root, right? So this is just going to be the integral. Oh, I can pull out the 1/2. It's a constant. The integral from 0 to 9 of the integral from 0 to y divided by 3 of, well, it's the square root of y squared minus 9x squared squared but when you square the square root, as I just mentioned, you just get y squared minus 9x squared. Oops. Right. Okay, and so now we're just down to two iterated integrals, which you've done before. So, right, so now it's no different than what we did earlier. So when we do this inside integral now, this inside integral here, with respect to x, y is treated like a constant, right? So the integral of y squared is x times y squared. And then the integral of 9x squared minus 9x squared is negative 3x cubed, right? 9 divided by 3 is 3. And then we just evaluate this between 0 and y over 3. And then we can do the y integral, right? Okay, so remember, we're plugging in x equals y over 3. So we plug that in here and in here. So what are we going to get? We're going to get, let's see, y times y squared is y cubed over 3 minus 3 times y over 3 cubed. So a little bit of algebra there, but it's y cubed, and this is y cubed over 3 minus y cubed over 9. Yep. So essentially y cubed times 1 over 3 minus 1 over 9, which I think is just, if you multiply this by 3, 3 minus 1 is 2, 2 over 9, right? So 1 over 2 times 2 over 9 times the integral from 0 to 9 of y cubed. And now this is just a standard single definite integral. You can cancel the 2's, I guess, right? 1 over 9. And when you integrate y cubed, you get 1 over 4 y to the 4th. And now we just plug in 0 and 9. Yeah, we integrated already. There's no dy anymore, right? So yeah, you just get 9 to the 4th minus 0 to the 4th. So that's why I'm going to leave the 1 over 9 here, because this is just 9 to the power 4 divided by 9 to the power 1. So that's 9 to the power 3 divided by 4. And I think that's 729 over 4. So that should do it. Right, so what does this number represent, right? So this iterated integral here is 729 over 4, just some number. Right. Well, again, this defines a region Q, which we can try to interpret if we want. But the function f of x, y, and z turns out to only be a function of just z. It's just z, right? So think about the density as only varying with z. The bigger the z, the higher the density. So as you go up, the density increases, right? On the xy plane, the density is actually 0 because that's z equals 0, right? So you can have a density of 0. Unfortunately, if you go below the xy plane, then the density would be negative, and that's not a physical, realistic quantity then. But then you interpret this, instead of the density, maybe some other quantity. Like what can be negative, temperature, just anything that can be negative. You can have a physical interpretation of that, right? So yeah, in this case, the function we're integrating here is just z, right? And yeah, we're not going below the xy plane here, right? This is z equals 0 is the lowest boundary. That's the xy plane. And then what is z equals the square root of y squared minus 9x squared? Again, that should not be hard to figure out. It's 9x squared minus y squared plus z squared equals 0. So this is a cone. This is a cone in the y direction. So this is not going to be easy to graph here, but it's a cone that kind of looks like this, going sideways here, right? Because this is the y, it's right, the axis of rotation is the y-axis, right? And it's not even a circular cone, it's an elliptical cone. So, right. So that's the surface, and then again, we're only going between x equals 0 and, or sorry, y equals 0 and some line here. This is x equals y over 3, or y equals 3x. So between 0 and that, and then, oh, y equals, so I got that backwards, right? And then y goes from 0 to 9. Yep, so here's 9, here's 0. So it's the slice above the cone, or sorry, but above the xy plane, but below the cone. So the cone is only the upper half of the cone here. All right, terrible picture, but again, that wasn't the question. The question was just to evaluate the integral, not to interpret the region. It's going to be pretty tricky to draw these in 2 dimensions for me. So apologies in advance. Okay, so here is an actual triple integral. They give us the function that we're integrating over here. F of x, y, z is just x squared times y times z. Okay, and the region Q is given, well, by this description here, this set of points in the, right, in x, y, z space. Right, so we just use Fubini's theorem and change this into an iterated integral. Right, and so we don't even need to draw the region. It might be helpful in some cases, but I think in this case, let's just try to evaluate it, right? So x goes from 0 to 2, y goes from 0 to 2x, and z goes from 0 to y squared. And now we're just integrating x squared yz, well, dz, dy, dx, since that's the correct order, that's the best order here, right? Right. So now it's just the same as it was in the previous examples. We do the inside integral first. So from 0 to 2, 0 to 2 over x, we'll do that later. And now we're just integrating z, so we get 1/2. I'll pull the 1/2 out. Yeah, the equal sign here. Right. So we have x squared y z squared, but the z is evaluated between 0 and y squared. Right? So that's just going to be 1/2 the definite integral from 0 to 2 of the definite integral from 0 to 2x of, well, x squared y, and then y squared squared is going to be y to the 4th, right? But y times y to the 4th is y to the 5th. Okay. And now we just have to evaluate this inside integral here. So that's the y integral now. So the integral of y to the 5th is 1 over 6, right, y to the 6th, evaluated between 0 and 2x. So I think we get 1 over 12 for the constant on the outside. And then just the definite integral from 0 to 2 of x squared times, well, 2x to the 6, right, minus 0 to the 6, which is 0. Yeah, so 1/12 the integral from 0 to 2. So 2 to the 6 is, I believe, 64. And then x squared times x to the 6th is x to the 8. Okay, so we're getting some pretty big exponents here, but that's inevitable. that happens sometimes, right? So 64 over 12, the integral from 0 to 2 of x to the 8 dx. And let's see, 64 divided by 4 is 16, and 12 divided by 4 is 3. So the 64 over 12 just reduces to 16 over 3. Sorry, 64 over 12, yes, 16 over 3. Right, now we can do the integral. X to the 8, we get 1 over 9 times x to the 9, evaluated between 0 and 2. So let's see, 16 over 27 times 2 to the 9th. And 2 to the 9th is, I believe, 512. Well, but let's see, this is 2 to the 4th. So this is 2 to the 13th divided by 27. Right, 9 plus 4 is 13. And 2 to the 13th is 8,192 divided by 27. Or if you prefer, it's about 303.4074 as a decimal approximate. Okay, so again, what does this number represent here? This 303.4 approximate? Well, it represents either the four-dimensional volume underneath this region Q here, and by underneath I mean in 4 dimensions, so forget that. Or you can interpret this to be like a density function, and you're just adding up the different densities at each point, and you're getting the total mass, right? Again, that might not work if this is a negative number. Then I don't know what negative mass is, but then shift your interpretation to something else, like maybe temperature, right? But since we got a positive number, we can think of this as the mass if this F represents the density at each point x, y, z in space. Okay, so again, this number is the mass, but the mass of what, right? Some three-dimensional object, right? So what does this object look like? So for that, we look at Q. And so I'm going to do the best I can to do a graph of this. So the real trick is to figure out how to orient your axes here. So I'll leave the z-axis vertical, but I don't think I want to do this to be my x-axis. I think I want, let's see, maybe this to be my x-axis, this to be my y-axis. Okay. Because, yeah, x is going from 0 to 1 to 2. And, oh, okay, let's try that again. Say this is 1 and this is 2. Because y is going from 0, which is just the x-axis, right, to y equals 2x. 1, 2, 3, 4. So this is the line y equals 2x. So already we're above this little triangle here. So this region here, above that triangle. And now what's the actual surface above that? It's the cylinder, z equals y squared. So z is equal to y squared, right? So that's going to be a parabolic cylinder. And it's going to look like this. Maybe I'll exaggerate a little bit here. Now we don't need this piece of it on the left because remember y is positive, x is positive here, right? But then there's also this. So here is the portion of the parabolic cylinder from x equals 0 to x equals 2. However, we only want the piece of it that's over the triangle. So what happens is we're going to cut this off here and just get this piece of it here. So we're talking about this surface right here. And that's the top piece of the surface, right? This goes all the way down to this point right here, which of course is the point 2, 4. So the solid region is below this red surface, but above the green triangle. Makes sense. It's all of this in here. Right, and it's very low down here, but it's higher up here. So again, not a great picture, but that's the Q. That's the volume we're looking at here. And remember, this is not the volume. This is just the mass of the object, where this is the density. Right? So the density, remember, was, I think it was x squared yz, right? Yep, x squared yz. Right. So as our third example, and I thought I would try an easier one, find the volume of Q. Right. Volume. Let's try that again. Volume of region Q. Right. So we did the hard part in the last problem. We got the limits of integration, right, using Fubini's theorem. So we're using the same limits here, but now instead of integrating x squared yz, we're just integrating 1. So the volume will just be the triple integral from 0 to 2, and then from 0 to 2x, and then from 0 to y squared. But now we're just integrating 1 dz dy dx, same order of integration. Right? So when you do the first integral, when you integrate 1, you just get z, evaluated between 0 and y squared. So that's just going to be the double integral from first from 0 to 2, then from 0 to 2x of y squared. Right. And now, when you integrate y squared, you get 1/3 y cubed, and we're just plugging in 0 and 2x, right? Oh, so we don't need, right? Yeah, we did the integral. We did the integral, right? So the 1/3 can come in front. That's a constant. And then we're just integrating 2x to the power 3, right, minus 0 to the power 3, which is 8x cubed. So bring the 8 outside. And when you integrate x cubed, let's move it up a little, what do you get? You get 1/4 x to the 4th evaluated between 0 and 2. Okay, so 8 over 4, so we get 2 over 3, times 2 to the 4th power. 2 to the 4th is 16. And, yeah, 60, right, so I canceled these, right? So 16 times 2 is 32 over 3. Okay, so that's oh, sorry, that's not the mass. That's the volume. That's the volume, right? This is the mass, the 8192 over 27. Okay, so there you go. That's just the volume of the region Q here, volume of Q. All right, so again, most of the integrals here are not going to be much trickier than this. You know, oh, once in a while you might need to integrate by parts, so keep that in mind, right? Or maybe use a trig substitution or something like that. But I think the book tries to keep it simple, and I will as well. Okay, so as promised earlier, we said we'd do a problem finding the center of mass and moment of inertia. So, right, Q is the solid region. X goes from 0 to L, Y goes from 0 to L, and Z goes from 0 to 2L. So, of course, this is our Q over here. Right? It's just a box, a rectangular box, where the height is twice the length and width, right? So the length and the width are both L, and then the height is 2 times L, right? L is just some number, right? It's just the length of the base here, right? So that's the region, solid region. And now we want to find Z bar. So what about X bar and Y bar? Well, that part, we're gonna do this very quickly here, because notice that if we graph the XY version of this here, right? So we're looking from above, look straight down, and we see this square here, right? And notice that the density only depends on z. It doesn't depend on x and y. So this square here is uniformly dense in all directions, right? It's a constant density, right? Right. It will increase, the density will increase with the height, but not with the length or width. So where do you think the center of mass is going to be, right? Of course, it's got to be right in the middle. It's got to be right in the middle, right? So x bar has to be L over 2, and y bar has to be L over 2. So this is by just considering the symmetry of the situation here, of the picture. Okay? Now, using symmetry, then you might conclude, well, wait a minute, isn't then z bar just going to be, well, since the height is 2L, it would just be L. It would be right in the middle, right? It would be, yeah, right here in the middle. Yeah, be careful because the density increases as you go up. It's more dense at the top than it is at the bottom. So as you go down, it's less dense, but it's more dense up here. So I would expect that that z bar will be a little bit higher than L, than halfway up. Okay, exactly how much? Well, we'll have to do the math and calculate it, right? But there's no symmetry with respect to the z-axis, right? The z-axis is very low density down here, it's 0, and then it's very high density up here. So as the density increases going up, we don't expect symmetry here, right? So z bar is probably not going to be just L, which is half of 2L, right? 2L over 2, as you might expect, as we did for x bar and y bar. Okay, so we actually have to calculate z bar. And remember what z bar is. It's 1 over m times the triple integral of z times the density, which of course the density is just z. Right? So it's going to be 1 over m times the triple integral of z squared, z times z, right, over q. But of course, what's m? So we have to calculate m. M is just going to be the triple integral of the density, right? And the density, again, is just z. So now we're just integrating z. And the limits of integration here are just going from 0 to L. So that's x, 0 to L for y, and then 0 to 2L for z, right? And when you integrate z, of course, you just get 1/2 z squared. I'm going to try to squeeze it all in here, because this should have been the easy example. So z squared evaluated between 0 and 2L. And then that's going to be 4L squared. So you're going to get 2L squared on the outside. And then that's it, right? This is just 1 dy dx. So I think you can handle this integral here. You're just going to get L. And then for the x integral, you'll get another L. So I think we get 2L to the 4th. Okay, so that's the mass, right? That's m. So keep that in mind. Now we can find z bar, right? The z coordinate of the center of mass. Right? So it's 1 over m, 1 over 2L to the 4th. And then this triple integral. Again, 0 to L, 0 to L. But now we're integrating z cubed, right? From 0 to 2L. Sorry, z squared. We're integrating z squared, right? Which means we get 1/3 z cubed. Right, so yeah, so 2L cubed is going to be 8L cubed dx, right? I'm trying not to skip too many steps here. I don't want to lose anyone, right? So this is going to be, yeah, 8L cubed over 6L to the fourth. And then we have the same double integral from 0 to L of 1 dy dx. So luckily, we know that that's just L squared, right? So 8 over 6 reduces to 4 over 3, and then L cubed over L to the fourth is just L, and then this becomes L squared. So we get 4 over 3 times L. And that's Z bar, right? That's our Z bar. So, right, so as promised, it's bigger than just L. It's a little bit higher than halfway up, right? If this was, right, if this density here instead of Z, if this were just a constant, then you would expect Z bar to just be L, right? Which is halfway between 0 and 2L. But here it's a little more than halfway in between, right? So putting this all together, right, the center of mass, right, your X bar, Y bar, Z bar, is just going to be, right, L over 2, and then 4L over 3. So that'll be the location of the center of mass. Okay. Right. And in this case, they really just wanted Z bar. We're not calculating X bar and Y bar by hand because, again, it's just a tedious calculation, and we can get it by symmetry here. Just be aware of when you are allowed to use symmetry and when you're not, right? You're allowed to use symmetry when the density doesn't vary with X or Y. So, yeah, if the density function, right, were given as something like x times y squared times the square root of z, then because it depends on x and y, your center of mass won't be right in the middle anymore. So yeah, so symmetry only works in certain cases, right? When the density is uniform, essentially. Right. Okay, oh, and they want IZ. They want the moment of inertia about the z-axis. Fair enough. So IZ, the formula for that, it's on your formula sheets. It's just the triple integral of x squared plus y squared times the density, which we know is z, times dv. And so this might be a more complicated integral than I had anticipated, but we'll work it out, right? So the limits for q are the same as they were earlier. So let's just fill those in. 0 to L for x, 0 to L for y, and then 0 to 2L for z. And yeah, when you multiply this out, you get, well, actually, we don't have to multiply it out, right? X squared plus y squared will just be a constant for now. And when you integrate z, you get 1/2 z squared. Oh, sorry. I still wrote the integral here. Oh, I guess I'm just copying it down, right? Oh, I'm putting in the limits. Okay. Fair enough. So yeah, when you integrate z dz, you get 1/2 z squared. Evaluated between 0 and 2L. But we can do this in our heads, right? This is just 4L squared. 4L squared, right? Which is a constant. We can take that out as well. So that'll be 4 over 2 is 2L squared. And now we just do the integral from 0 to L of x squared plus y squared dy dx. Okay. So we'll do this integral next. Leave the 2L squared. And when you integrate with respect to y, you get x squared times y plus 1/3 y cubed, evaluated between y equals 0 and y equals L. So we still have the x integral to do. All right. So remember, these are y's, so it's not L squared. It's going to be Lx squared plus 1/3 L cubed. And finally, we integrate with respect to x. So that's going to give us 1/3 Lx cubed plus 1/3 L cubed times x, evaluated between 0 and L. So let's see, 2L squared, what do we get? We get 1/3 L to the 4th plus 1/3 L to the 4th is 2/3 L to the 4th power. And multiplied by 2, you get 4/3 L to the 6th. Yep, so that's the moment of inertia rotating about the z-axis. Obviously, you're not going to get the same thing if you revolve around the x-axis or y-axis. But yeah, so if you take this object here, this Q, and you rotate it around the z-axis, this is sort of the inertia. This is how difficult it will be to rotate it. Right. Okay. Yeah. Oh, and if you're wondering about, wait a minute, what the units here are L to the 6, right? So that's meters to the 6th power. How is that possible? Right. So what are the units for moment of inertia? Again, just to give some continuity with your physics course here, right? You're basically getting a mass times, right? So this is mass times a length squared. Okay. So it's a mass times length squared. So the units, the usual units are kilogram meter squared. Okay. So remember what the mass was. The mass was 2L to the 4th. So somehow our units are getting kind of mixed up here, right? We're not really using proper units here in terms of the, the density obviously cannot be z, right? So the density z here is really, kilograms per cubic meter, right? So yeah, it's really kilograms per quartic meter times z gives you kilograms per cubic meter. Anyways, not to worry about that. I'm not going to worry about units here, but since mass is L to the 4th, right, this is where we get L to the 4th times L squared, we get L to the 6th. So obviously not the correct units for moment of inertia, but if you did kilograms, right, per quartic meter earlier, then you would get the correct kilogram meter squared, because the meters to the 6th will cancel with meters to the 4th. But let's not worry about units here, right? And in this class, our units are just going to be numbers. And L is a number, right? L could be, 5 meters or something. So, yeah, so let's not worry about units here. But yes, in a physics or engineering class, make sure you, put in the proper units, whatever they are for your particular example. Okay, so again, just a good example of calculating triple integrals in terms of finding the mass, the center of mass, or moment of inertia. Okay, we're going to do one last example. And I'm kind of dreading this. I am not a fan of these particular questions. So you're not likely to see these on a test, although you never know. I certainly, I think there's one or two of these in the homework, and I would highly recommend you doing them regardless, just to get the idea, right? Because this will involve graphing here. We're going to graph a solid three-dimensional region. Just do the best you can, right? And mine's not going to be great either, but I will try my best. And you might say, well, can I just switch the order without graphing the region? I can't do that. You have to visualize the region then, right? Because remember, switching the order is not just switching these around here, right? We saw that when we did the double integrals and changing the, all we did was change dy dx, to dx dy, right? And remember, that was not trivial. That was complicated. And to do that, we did graph, the region in the xy plane, and that's not hard to do. But now we're graphing regions in space. So that becomes a little bit trickier here. Put that back. All right. Well, yeah, so this represents the volume of something, right? This is the volume of some region Q. So let's see if we can write Q, right? And the reason why it's a volume is because we're just integrating 1, right? There's no function in here, so this will be a volume. And we don't have to we don't have to evaluate the triple integral here. We could try if we want. I'm not sure it's an easy one to do, but we could, but that's not the question. Right? The question is to sketch the region and switch the order, not to actually evaluate it. Yeah, so read the question carefully, because if this were on a test and you spend a lot of time working through this integral, evaluating it, that's not the question. You're answering the wrong question. So again, read the questions carefully here. Okay, so just to get a handle on this, let's see if we can express this region as a set of points x, y, and z, right? So z just varies between 0 and 6 minus x minus y. And you should know what that is. Right? Y varies between 0 and the square root of 9 minus x squared, and I think you know what that is. And of course, x varies between 0 and 3. So this is not a hard region to understand here, especially if you just look at the region underneath the surface, right? Let's look at that first. Right. So x goes between, let me try to do a vertical y-axis here. It's a little bit better. Right. So y goes, well, from 0 to the square root of 9 minus x squared, and x goes from 0 to 3. Right. So, yeah, so what is this? Y equals the square root of 9 minus x squared. If you rewrite it, you get x squared plus y squared equals 9, which is, of course, the circle of radius 3. Let's try to do a circle. Right. And again, it keeps going everywhere else here. But remember, y goes from y equals 0. This is the x-axis. And x only goes from 0 to 3. So we're talking about just the quarter circle here. Right. So yeah, x goes from 0 to 3. Y goes from 0 to, well, this circle here, right? This curve here. Okay, but that's not what we need to graph. We need to graph the entire three-dimensional region. Okay, so that's not going to be quite as easy, but I'll do the best I can. So here's the z-axis. And let's do, this is the y-axis. Let's make this the x-axis here. And we can see if this is just 1, 2, 3. Let me space it out a little bit better. 1, 2, 3. 1, 2, 3. Now we can graph this region here. This is the circle, right, in the xy plane. So let's see, what color should I use here? So this is the region that we graphed over here. Oh, I can't fill in the entire space, but you get the idea, right? So that region is just in the xy plane here. Right. You can call it region R if you like. Okay, now sitting above all this is this surface here, z equals 6 minus x minus y. And I said earlier you should know what this is. It might be more familiar if we add the x and y to both sides. X plus y plus z equals 6. Of course, it's just a plane. It's a plane in space, right? And in particular, when x and y are 0, z is, well, 6. So 1, 2, 3, 4, 5, 6 up here. Right? And notice that if x and z are 0, then y is 6. So 4, 5, 6. And if y and z are 0, then x is 6. So 4, 5, 6. Right? So we can think of these 3 points here as the 3 corners of the plane. Oops, 6, 0, 0. And this will be 0, 6, 0. Okay? So the plane stretches this way. I don't think it touches the circle. Nope. So, yeah, so this point right here might just be, 3, 3, 0, right? 3 plus 3 is 6. Yep. But this distance here will be less than 3. In fact, that's the radius, right? So, yeah, the distance to 3, 3, 0 would be, what, square root of 18? Which is bigger than 3, I think. Okay, so this is the plane, right? This is the plane z equals 6 minus x minus y. All right, so what is our solid region here? Our solid region is going to basically be what's under the plane here, underneath this plane, but above the region R, right? So the region R, this hits the plane right around here. Maybe I made this a little too dark. That's a little lighter, right? So, yeah, so this plane here is just this straight plane, right? This is the top piece of it sitting above the region R here, right? So this is really not that bad here. This is not too bad, right? This is the side. I shouldn't use the same color. Right. This is essentially the side of it here, right? So one piece of it here will just be sort of cylindrical, right? And remember, we're only getting a quarter of the cylinder here, right? But then instead of this being flat here, we have this little piece of it that's just the plane extending above it, right? So I think I said this was straight. It's actually like a cone, right? This yellow piece here is really part of a cone, I think. Is it? No. It's a plane. It's straight. I'm sorry. It's not a cone. Yeah, it's hard to visualize here, right? Because this intersects on a circle, but it's still straight. It's still straight. It's still a flat plane. So this piece is flat here. It's not curved. I don't think. I'm trying to visualize, right? So yeah, because this is right. You swing this about this way, and it looks like it's a surface of revolution. But a cone is curved and a plane is flat. So this is flat. Right? The top piece is definitely a plane, not a cone. Okay. So again, hard to visualize, but that's the region Q here, right? That's the region Q. So that's only part of the problem. Right now we have to switch the order of the integration, right? So what we're given is dz dy dx. We want dz dx dy. And this shouldn't be that bad because you're just switching x and y. You're leaving z alone, right? So to do this, all we really need to do is look at this figure here on the left, the two-dimensional region R. Right? So how do we switch the order from dy dx, which are it's a vertically simple region using vertical rectangles, and now we want to switch it to horizontal rectangles. Okay. So yeah, just ignore the z for the moment. We'll put that back later. But we have dy dx, right? And we want to switch to dx dy. Right? So what are the limits here, right? For y, it's 0 to the square root of 9 minus x squared. And x goes from 0 to 3. Right? but that's looking at this curve being a function of x. Now we need it as a function of y, right? So just take the inverse. In other words, solve for x. X squared is 9 minus y squared, and when you take the square root, you get plus or minus the square root of 9 minus y squared. Well, we don't need the negative square root because that would be where x is negative over here. But remember, x is going from 0 to 3, so we only need the positive square root here. Right. So yeah, x is going from x equals 0 to x equals the square root of 9 minus y squared. And y is just going from 0 to 3 now. So no surprise, it looks almost identical to this, except we switch the x and y, obviously. And now, to put back the z integral, we'll just put it back. I don't think anything else changes here. So the inside integral is still 0 to 6 minus x minus y dz. But now, these are x's and these are y's. So this is x equals 0, y equals 0. So we switch the order to dz, dx, dy. Okay, so that's the answer to switch the order of integration. Okay, generally not an easy thing to do, especially if you want to switch, to a weird order like dx, dz, dy. That's a hard problem. And as a challenge, you could try that. But generally, I'm like I say, I'm not a fan of having to do this, switching the order like that. Again, the order in which we prefer it is right here. dz, dy, dx is the easiest one because that was the Fubini's theorem we talked about earlier. If you go back and when I talked about how do I change, right, a triple integral, although f is 1 here, to an iterated integral, and you use Fubini's theorem, right? But this depended on z being a function of x and y being some function of x, and then x just varying between two numbers, right? Like x is between, a and b, for example. So yeah, when they're given this way, it's very easy to determine the surface. And that's the way this was given, dz, dy, dx, right? So to change the order, I don't know why you would ever really need to do that. I mean, I guess to make the integral easier, maybe, but, not so much in this case. Well, we did have to change the order in the two-dimensional case, right, for double integrals. In some cases, to make the integration doable, right? Because remember, in one order, the integration might have been impossible. Like here's an example of that, right? I don't know how to do this integral, but it turns out that if you're doing the double integral, if you somehow switch the order of integration and do x first, then because the 1 plus y cubed is constant with respect to x, right, you'll get an extra, you'll get an extra factor of, say, y squared here, and then it'll be doable using substitution. So that's one reason why you might need to change the order. But notice the integrand here is 1. So in this case, that issue is not really going to come up that much. So yeah, so maybe try one more of these, see if you can do it, and do the best you can with graphing it. But yeah, not terribly simple. And the next thing we'll do, of course, is instead of using rectangular coordinates, x, y, and z, we'll use cylindrical and spherical coordinates. So when when either the region or the function you're integrating depends on, say, rho, phi, and theta, or r, theta, and z, then you might want to switch to rectangular or from rectangular to spherical or cylindrical. Because so far, all we've done was rectangular coordinates, which, again, is nice when you can do that. But, in some cases, it might be easier to switch variables.